Hello, I'm to explain you about the LC oscillations. So you can see here what do you mean by LC oscillations. In a LC circuit, there will be the energy change from just it. Now, in an LC circuit, there will be the interchange of energy from inductor to the capacitor. As we know that when current flows to the inductor, when current is flowing to the inductor, that is through the coil, there will be what type of current? So there will be not current. When current flows through the inductor, there will be what type of energy will be stored here? There will be the magnetic energy. Magnetic energy will be stored here. Magnetic lines of force will develop. Similarly, when the capacitor is in the charged state or when it is charging, what will happen? During the charging, an electric field will develop within the plates, in between the plates of the capacitor. When it is charging, electric field will develop in between the plates of the capacitor and the energy will store in the form of electric potential energy, while here it stores in the form of magnetic energy. In an LC circuit, if there is an ideal LC circuit, there will be a continuous change of electric potential energy into the magnetic energy and from magnetic energy to the electric potential energy. This continuous conversion of energy from one form to the other in an LC circuit is called the LC oscillations. It's called the LC oscillations. Here energy changing from one form to another. And during this interchange of energy, what will happen? The current which is flowing through the circuit, that will also change from 0 to some peak value. Then it becomes 0. After that, direction will be changed. Once again, in the reverse direction, it will become maximum and then from maximum to 0. So what is the meaning of LC oscillations? You can see here, when a charged capacitor is discharged through an inductor of negligible ohmic resistance, so that there is no loss of energy. In the ideal case, we have assumed its resistance 0. Therefore, there is no loss of electrical energy. I square RT equals to 0. As you know that if there is a resistance, if there is some resistance, then what will happen? Current, on flowing the current, electrical energy will change into heat energy because of the resistance. It's clear. So, of negligible ohmic resistance, electrical oscillations take place in the circuit. What is the meaning of these electrical oscillations? It is the interconversion of energy from one form to another form. It's clear. And during this interconversion of energy from one form to another, what happens? Current increases from 0 to a peak value, then becomes 0, then it will reverse the direction, and in the same way, once again it becomes maximum, and finally it becomes 0. There will be the variation of the current. So you can see here in the diagram, here this is a capacitor, this is the inductor, and here there is a switch S, which can be connected towards A and it can also be connected towards B. This way also you can connect. You can disconnect from there and connect it to A. It's clear. So here you can see. Now initially this capacitor is connected to this cell, this battery. When it will be connected to the battery, what will happen? Capacitor will be immediately charged. it will be immediately charged, means you can see from here when it will be connected to the battery. I am showing it you here. This is the battery. When it is connected, capacitor is connected. Suppose the potential difference is of 2 volt. What will happen? It will start charging and a stage will reach at which its potential difference will become 2 volt. And when potential difference will become 2 volt, what will happen is it will stop charging. Charging will stop, and charging will stop means the current will also become zero. Current will also becomes zero. So as soon as you will connect the capacitor across a source of EMF, what will happen? It immediately charges instantly. It instantly charges and acquires the same potential difference between the plates, which is of the this cell, which is the terminal voltage of this cell. It's clear? And at that moment, here energy will be stored in the form of electric lines of force, which will be directed from positive plate to the negative plate. Positive plate to the negative plate. So you can see. You can see. Yes. When it is connected, so here there is a capacitor. Here this switch is connected to A. So capacitor will start charging and it will be charged up to the potential difference of this cell. It's clear. Suppose its potential difference V, then it will charge up to that potential difference. And here we have assumed that it has acquired how much charge? How much charge has it stored here? Q naught. When it is fully charged means what is the meaning of fully charged? When the potential difference between the plates of capacitor is equal to the terminal voltage of this battery, then it will be fully charged. Let at the fully charged state, it has what charge on each plate? Q naught. So what will be the energy stored here? Energy stored will be here. It will be given by, as you know that in capacitor, energy stored is given by U equals to Q square upon 2C. So since it has acquired Q naught charge, so it will be Q naught square upon 2C. It's clear. So you can see here it has acquired this much charge. Now, after this, what will you do? You will disconnect this switch S and bring in contact of the this. Bring in contact of the B. So see here, what will happen? Now it will not be connected to the battery because now there is no connection in this side. Here there is no connection. It is connected to the inductor. Here it is fully charged. So what will happen? Because of that, it is fully charged, there is a potential difference V. Because of that potential difference, a current will set up in this. A current will set up in this circuit, which I am showing here. It's clear. Current will start flowing in this direction, this way. It's clear. It will start flowing in this. Here it is shown. In this diagram, it is shown. Here current is flowing in this way. So now what will happen? Since here it is now disconnected from the battery, therefore its potential difference will decrease because the magnitude of charges, level of charges decreasing, level of charges decreasing, and that current which is flowing here, the current which has increased from 0, it will keep on increasing. It will keep on increasing. It's clear. And a stage will be reached when capacitor is totally discharged while whole current in the inductor is maximum. Means during the start of discharging, current was almost 0. As it discharges more and more, what will happen? The magnitude of this current will increase. The current through inductor will increase. The magnitude of charge, the level of charge of in the capacitor will decrease. And since level of charge is decreasing, therefore potential difference is decreasing, and a stage will be reached when this potential difference will become zero, and at that instant it will be totally discharged. It will be totally discharged, and current in the inductor will be maximum. What will be the energy stored? Suppose the peak value of current is I naught. So what will be the energy stored in the inductor? It will be given by 1 upon 2 L into I naught square. 1 upon 2 L into I naught square. Now see here, when it has become zero, you can see here, when the potential difference across the capacitor has become zero, then here current is maximum. Now what will happen to that current? That current will not immediately become zero. It will not immediately become zero. It will, since now there is no support for the current, so what will happen? It will start decreasing. It will start decreasing, but flowing in the same direction. According to the Lenz's law, it will flow in the same direction. It's clear. During discharging, the current which is produced because of the self-induced EMF will flow in the same direction as the direction of main current. So here it is given by Lenz's law, the dying magnetic field induces an EMF in the inductor. That is called the self-induced EMF. And this self-induced EMF will set up the current in the same direction as it was flowing previously. So the current continues to flow in the same direction. You can see here it continues to flow in the same direction, and capacitor is again charging in the reverse direction. Again charging in the reverse direction means what will happen? Now this plate will become positive and this plate will become negative. You can see here. If you see here, now the polarity of the plates has changed. This plate, positive plate, has become negative and negative plate has become positive. What will happen to the current? Current is decreasing from I naught. It decreases from I naught and becomes zero when inductor is, the magnetic field within the inductor is zero. When magnetic field within the inductor is zero, then at that instant current will become zero and capacitor will be fully charged. And if we assume that there is no resistance of this inductor, means there is no loss of energy, therefore it will charge to the same potential as of this. As of this. And in that case, what will be the graph of current versus time? Current versus time graph will be this. There will be same magnitude of current. Magnitude of current will remain same. It will not decrease. And why it will not decrease? Because resistance is zero. But as you know that it is not possible, resistance will always be zero, and resistance will not be zero. Resistance can never be zero in case of coil. So what will happen? There will be the loss of energy, continuous loss of energy. And when there will be the loss of energy, what will happen? The magnitude of current decreases during this repeated cycle of charging and discharging of capacitor. What will happen? You can see during this repeated cycle of interconversion of energy from one form to another, there is a continuous loss of energy I square RT. Continuous loss of energy I square RT. You can see writing here R is the resistance of the coil. It's clear. And because of this, what will happen? The magnitude of current will decrease. And when magnitude of current will decrease, you can see here, accordingly, the current in LC circuit first rises from 0 to the maximum value in one direction, reduces to 0, then again rises to the same maximum value in the reverse direction, and again reduces to 0. It's clear. You can see here. When it will be fully discharged, when it will be fully charged in the reverse direction, current will start flowing. The current which is flowing here, you can see here. When it is fully charged in the reverse direction, when it is fully charged in the reverse direction, what will happen? The same thing will take place. The current will start flowing in this direction. It's clear. It will flow from this plate to this plate, as I am showing here. Means opposite to this direction. It's clear. Means it will start flowing in this direction, and its magnitude will continuously increase and becomes maximum here. It's clear. Means current is flowing in opposite direction becomes maximum. It's clear. You can see here. Accordingly, the current in LC circuit first rises from 0 to a maximum value in one direction, reduces to 0, and then reduce it to 0, then again rises to same maximum value to the reverse direction and again reduces to 0. But it will rise to the same maximum value only when the resistance. If there is some resistance, then what will happen? There will be continuous loss of energy and the graph of current versus time will be like this. It's clear. What will be the natural frequency here? Natural frequency of these oscillations, it is given by F equals to 1 upon 2 pi root LC. 1 upon 2 pi root LC. You can see here. It will be this 1 upon 2 pi root LC, which has been written in this form. It is not needed. You only remember this form 1 upon 2 pi root LC. Now about the resonant circuit, I have told. There are some graphs that I am going to tell you. As you know that in LCR circuit, resonance takes place when the frequency of applied AC EMF is equal to the natural frequency of LCR circuit, which is given by 1 upon 2 pi root LC. It's clear. So all these things I have explained. During the electrical resonance, what will happen? Circuit will behave as a pure resistive circuit. Its impedance will be minimum and the current will be max. Now, if we draw the graph of I versus F, this is the graph of I versus F. So you will find that in the graph of I versus F, it will be like this. It will be maximum. You can see here, I am showing you here. If you see here, if we draw the graph of I versus F, what is F? F is the frequency of applied AC voltage. It's clear. And here, this is the F naught. F naught is what? It is the natural frequency of LCR circuit. You can see here. Here it is. You can see, wait a minute. Here, this is the, I am showing you. This is I am going to draw the graph of I versus F. Here in this side, I have represented frequency of applied AC EMF. F naught, it is the natural frequency of LCR circuit. So you can see that as long as F is less than F naught or F is more than F naught, frequency current will be less. Current will be less than at this, suppose at this position, at this level, when the frequency is equal to F naught, current is I naught. It's clear. So at these instants, when the frequency is this, when the case is this, when the case is this, current will be less than I naught. Means the graph will be like this. It will be like this. It's clear. This is the peak value of current, which is given by equals to V naught upon R or V upon R. Any way you can write. When the frequency of applied AC EMF is less than F naught or greater than F naught, less than F naught means this frequency F1, greater than F naught, you take this frequency F2, you will find that the magnitude of current is less than the I naught. So this is the graph of I versus F. Now if you draw the graph of Z versus F, impedance versus frequency of applied AC voltage. Here, this is the frequency, this is F naught. So when you will, this is not correct. What will be the shape of the graph? Shape of the graph will be like this. As already I have told, when F becomes equals to F naught, impedance will be minimum and it will be Z minimum will be equal to R. At other frequency means when F is less than F naught or F is more than F naught, impedance will be more than R. Impedance will be more than R. It's clear. So these things I have already told that in case of the series resonant circuit, electrical resonance take place when the impedance, when XL equals to XC, both the reactances are equal. Both the reactances are equal. Or frequency of applied AC EMF is equal to the natural frequency of LCR circuit. You can see here. There are some characteristics of the series resonant circuit. Resonant circuit means, you can see here. Resonant circuit means already I have told that when XL equals to XC, when the frequency of applied AC EMF is equal to the natural frequency of LCR circuit. In that case, there are here some properties, characteristics of the series resonant circuit. You can see. Number one, the applied alternating voltage and resulting current are in the same phase. Why? Because the circuit we have just the pure resistive circuit. Net potential drop will be equals to VR. It's clear. So VR and I both will be in the same phase. Impedance will be minimum. It will be equal to, or current will be maximum. It will be given by I equals to V upon R. It's clear. The potential difference available across this you can see the potential difference available across the inductance L and capacitance C may be higher than the potential difference applied to the circuit. Means the values of VL and VC may be higher than the net potential difference V, and that you can see from here. Here you can see. Yes. If you go see this one, here there is a example of some example is given here. You can see. Yes. For example, say in above circuit, R equals to 5, XL equals to XC equals to 20. So XL and XC are both are same. Therefore, what will be? It will be in the electrical resonance condition. It will be a resonant circuit, resonant LCR circuit, and the root mean square value of the applied voltage is given 100 volt. So what will be the current? Current will be equals to I equals to V upon Z, because here XL equals to XC, therefore it is a resonant circuit. So what will be its impedance? It will be equal to R, that is equals to 5. So what will be I? I equals to 100 upon 5, that is 20 ampere. Now, if you find out VR, VL, and VC. So as we know that VR equals to I into R. What is I? I 20 ampere. R is 5, 20 into 500 volt. What is VL? VL equals to I into XL. I is 20, XL is 20 ohm. So 20 into 20, 400 volt. It's clear. And what is VC? IXC, that is 20 into 20, 400 means you can see here. Here you are applying only 100 volt, but here you are getting 400 volt. I am showing in the diagram. You can see here. Here you have applied only 100 volt. 100 volt you have applied. 100 volt you have applied, but across the inductor you have got 400 volt. Across the capacitor also you have got 400 volt. Therefore, series resonant LCR circuit provides the voltage amplification. It provides the voltage amplification. You can see here. So the resistance of the circuit has no effect on the resonant frequency, provided it should be very small. Provided it should be very small. If it is large, then definitely it will be changed. It's clear. So this is all about the series resonant circuit. Now here you can see there are some graph of XL versus frequency. XL versus frequency. So this graph will be straight line. XC versus F, that already I explained here in the during pure capacitive and pure inductive circuit. These graphs already I explained. And the graph of impedance with respect to the frequency, it will be of this thing. It will be of this thing. It's clear. Parabolic thing. So now I hope that it will be clear to